This we will discuss emulsion, emulsifying agent, then miscellaneous applications and examples of colloids, okay, and then some problems. Emulsion. So emulsion, it is a type of colloid. When we have discussed different types of colloids, depending on the nature of dispersion medium, dispersion phase, then also we have already seen what is emulsion. But as this is very common, so that is why we will discuss it in detail. Colloidal dispersion of two immiscible liquids. So here dispersion medium and dispersion phase both are liquids, but they are immiscible, okay. So one liquid is acting as dispersion medium, another liquid will act as dispersed phase, depending on which one is present in higher amount. And this type of colloid is known as emulsion, where both the that is dispersion medium and phase both are in liquid state. Now generally, that is in most of the cases, it is observed that one of the two liquids is water and the other, which is immiscible with water, is designated as oil. Now the other liquid which is immiscible with water, that is called as oil. But when we are saying oil, don't think that is the typically when we say oil, the appearance that comes in our mind, it may not be so. So here it is a general convention that one of the liquid is water and the other liquid, it may be anything, which is immiscible with water. This condition must be present. If it is immiscible with water, then we will call it oil. Now depending upon the nature of this dispersed phase, that is whether water will be dispersed phase or oil will be dispersed phase, emulsion can be two types obviously. So one type is where oil is the dispersed phase. So it means what? As oil is the dispersed phase, so it will remain in lesser amount, and the medium is water. So here you can see the medium, it is in light blue color. This is basically the water phase, that is dispersion medium. And here we have some oil globules. So this is basically dispersed phase. Fine. Example is milk, where liquid fat globules, which is basically the oil, it will be dispersed in water. So water is present in higher amount because it is the dispersion medium, and the fat globules, that is the liquid fat globules, they will be acting as dispersed phase. And this type of emulsion is known as oil in water, because oil is present in lesser amount. So that is why oil in water, it is also expressed in this way, that is O/W. So if this is one type, the other type will be obviously the reverse, that is water in oil. Now water will be present in lesser amount and oil in higher amount. So in water in oil, here dispersed phase is oil and it is reverse, and this is oil. Here we can see the oil phase, it is shown with yellow color, and the water droplets, which are basically dispersed phase, these are shown with this circle. Example is cod liver oil. So in cod liver oil, water is dispersed in the cod liver oil, though it is called, that is together it is called cod liver oil, but the dispersed phase, that is dispersion medium, that is also cod liver oil, that is oil, the liquid which is immiscible with water. And this type of emulsion, it is expressed W/O. The first one is O/W, now W/O. So the first alphabet, that is actually the dispersed phase. O comes before W means it is dispersed phase, but W comes before O means it is the dispersed phase. Okay. Emulsifying agent. Now from the expression, it is clear that the agent which will help in emulsification, obviously that will be called emulsifying agent. Now, to know what is emulsifying agent, we have to first understand that how emulsions are actually prepared. As the two liquids are not miscible to each other, so obviously we have to do the mixing vigorously, okay, and it is possible only with high speed mixing machine or by using ultrasonic vibrator. That means we have to provide some mechanical force, otherwise vigorously mixing is not possible, and this process is known as emulsification. That is the process by which we are making emulsions, vigorous mixing of two immiscible liquids. Now, since these two liquids that are we are using for preparation of emulsion, they are completely immiscible. So there must be presence of some stabilizing substance which will help to maintain their stability, and this stabilizing agent is basically emulsifying agent, or we can also call it emulsifier, and its main purpose is to stabilize the resulting emulsion. Now, as there are two types of emulsion, oil in water and water in oil, so depending on what type of emulsion you are trying to make, the emulsifying agent will be different. If we want to make oil in water emulsions, then we have to use proteins, gums, natural and synthetic soaps, this kind of emulsifier. And for the other type of emulsion, we will use heavy metal salts or fatty acids, long chain alcohol, lamp black, which is basically carbon particle, etc. Okay. So when we are using emulsifying agent, it will form interfacial film between suspended particle and medium. That means between the particles of dispersed phase and the dispersion medium. So if it is oil in water emulsion, that means oil is present in lesser amount. So this blue region, it is actually water, and this region, that is the yellow colored region, that is basically oil. So now this emulsifying agent, if you see this polar head group, remember the structure of surfactant. So here heavy metals also fatty acid, suppose if we are using, sorry, it is for oil in water. So here natural and synthetic soaps are using, and remember what are the molecules of soaps? It has this kind of structure, that is polar head group, and there will be hydrophobic tail. So polar head group, they are facing towards water, and this hydrophobic chain, they are basically towards oil. Okay, so in this way basically the emulsifying agents are working, and if it is W/O, that means water in oil, that means oil is present in higher amount, which is yellow color, and inside we have water. So now the polar head group, they are facing towards this water. You can compare it with the reverse micelle. Fine. So this is the role of emulsifying agent. It forms interfacial film between these two immiscible liquid. So this is the interfacial film. Okay, it may be two types depending on whether it is W/O or O/W. Now when emulsifying agent, if it is not present, suppose you are not using emulsifying agent, what will happen? So this is the emulsion in the right hand side, okay, but gradually with time, without using emulsifier, these two phase, that is the two immiscible liquid, they will separate from each other. The dispersed phase particles of colloidal size combine together, resulting in the breaking up of emulsion into two separate layers. Okay, so now the dispersed phase particles, they will not remain suspended, they will combine together, their size will increase, and they will separate from the dispersion medium. So you can now see clearly two separate layers. So now basically the stability is lost, the left hand side picture. Okay, so that is why this is the significance of emulsifying agent. If we are not using it, this kind of, though it will not happen very quickly, it will take some time, but still it will not be stable. So this is the reason why we add emulsifying agent. Now we will start different types of applications of colloids. The first type is industrial applications. Smoke precipitation. Smoke, this is an example of colloidal solution, right? So how it is colloid? Here negatively charged carbon particles that are present in air, that means solid in air. So here air is the dispersion medium, dispersed phase is carbon particles, and this is also called aerosol. Now as this is a colloid and smoke, it also causes pollution. So these carbon particles, it can do another thing, it may condense water vapor on them. So now there is water film present on the carbon particles, and as a result the new kind of substance is produced, which is smoke. Smoke is basically the combined term of smoke and fog. Okay, so there is a thick layer of smoke and it is causing air pollution. So whether it is smoke or smoke, in both cases there is some problems that we will face. Now this smoke can be removed by the application of colloids. Okay, so how we can do that? When it will come out from chimney outlet, okay, it will let through a chamber which is containing plates having a charge which is opposite to the charge of the smoke particles. Now as we are using oppositely charged particles, there will be charge neutralization. Okay, so finally there will be, that is the carbon particles, it will be precipitated. So because of this charge neutralization, they will lose their charge. So there will be no repulsion between the carbon particles because now the charge is lost, that is same charge. Because of same charge there is repulsion, but if this charge is lost, they will come to each other and it will be settled down, that is precipitation. And for this process Cortell's precipitator is used. Okay, so in this precipitator, these are the smoke particles and finally they will be precipitated in the bottom. Okay, this is the first application. Paints and inks. Also it is not just industrial, it has also household applications. It is basically pigment particles, that is paint is basically pigment particles dispersed in liquids. That means it is a solid pigment particles which is dispersed in liquid. Then ink, which is used in newspaper printing, that is also colloid, and here carbon black, that is carbon particle is present in oil. And the inks, because there are different types of inks, the inks that we use in the ballpoint, the ink that we are using, that is actually not of liquid nature, it is actually gel, and gel is also another example of colloid. Okay, next, sewage disposal. Dirty and muddy water from the gutters and drainages, it is called sewage. Now sewage is colloidal solution. And how it is colloidal solution? Because the colloidal particles, it is suspended in the water. Okay, now this, how this is done? First this sewage water, that is the dirty water, it is taken in a tank, and the tank, it is fitted with electrodes. Now when we are applying electrical field, what will happen? There will be movement of the colloidal particles towards the oppositely charged electrode. Okay, and there will be charge neutralization, ultimately they will settle as precipitate. Now the dirt, that is the colloidal particles, they will combine together and they will settle as precipitate. Now this coagulated matter, that is the precipitate, that can be used as manure. And the clean water that is also separated, it can be used for irrigation purpose. So basically we are as if recycling the sewage water. Okay, so this is very important application. Both the component of the sewage, that is the precipitate, that is also applied in as manure, and also the clear water, that is the dispersion medium, that is actually the clear water, it can also be used for irrigation purpose. Leather tanning. Skin of animals, that is from which leather is made, it is also a colloidal system. Now this is very unusual, but see how it is possible. Here the colloidal particles are basically present, which is positively charged. Okay, so when we are trying to do the tanning, during this process the charged particles of skin, they will be coagulated, and it is possible when negatively charged material like tannin is used, and also sometimes compounds of aluminium and chromium is used. Okay, so in this way leather tanning is possible. Disinfectants. Dettol and Lysol form oil in water type of colloid. Remember, in the first slide we have already seen two types of emulsion, oil in water, water in oil. So Dettol and Lysol, which is very common as disinfectant that we use at home, at hospital, okay, it is also a kind of colloid. Metallurgical operations. Fourth flotation process, though it is that is the details of this process, it will be discussed in metallurgy. Okay, that is completely different chapter, but remember it is important process in metallurgy, that is the extraction of metals from ores. This process used for metallurgy of sulfide ores, and it involves the treatment of the ore in emulsion of pine oil. Okay, so this is application in metallurgy. Rubber industry. Latex, which is basically colloidal solution of rubber particles, and these are negatively charged. Okay, so rubber is obtained by coagulation of latex. So as it is negatively charged, it is treated with opposite charge, that is positive charge, there will be coagulation, and finally it will be called as rubber. So rubber is obtained by coagulation of latex. Latex is naturally obtained, and then we are artificially making it, converting it to rubber. And why it is possible? Because latex itself is colloidal in nature. So that is why coagulation is possible, because whenever it is colloidal, that means it will always carry some charge, and if charge is present, then coagulation is possible when oppositely charged particles are mixed with it. Photographic plates and films. Photographic plates or films are prepared by coating an emulsion of the light sensitive silver bromide in gelatin over glass plates or celluloid films. Thickening agent. Toothbrush, lotions, lubricant, coatings. So these are some of the examples where viscosity is very important. Now viscosity is that is the resistance towards the movement of the fluid. That means if viscosity is very low, then the movement of the fluid, that will be high. So it is also a degree of flowness, that is flowness will increase if viscosity is low. So when we are using all these substances, basically here viscosity matters. Okay, so suppose if just consider toothpaste, if it is very flowy in nature, obviously there will be problem. So that is why here viscosity should be very high. So how to control this viscosity? That depends on what type of thickening agent we are using. So all these substances, it contain some component which is added to this to maintain the viscosity, and these substances that are added to control the viscosity, because in some cases it is required that viscosity should be very low, that is the degree of flowness will be very high. In some cases it may be required that viscosity should be high, that is degree of flowness it will be very low. So depending on that, how we can control it by adding some colloidal substances. Okay, so they are called as thickening agent, because by using these agents we are basically controlling the viscosity of the material. Natural applications of colloids. Now we will see that is the examples in day-to-day life in nature. Fog, mist and rain. All these are very common. Fog and mist basically we see in winter at night. What happens when temperature is very low? The moisture from the air, it condenses. So there will be condensation on the surface of these particles, forming fine droplets. Okay, on the surface of some, you can consider dust particles. Now when it is forming droplets, it is being colloidal in nature and it can flow in air in the form of mist or fog. Okay, now next, if we consider clouds, that is, we are basically discussing rain, but how rain occurs. Clouds are aerosol, so there will be presence of small droplets of water suspended in air. Now when clouds are condensed in the upper atmosphere when temperature is low, then these colloidal droplets will combine with each other. They will increase in size. It will be bigger and bigger, and ultimately because of gravity it will come down in the form of rain. So that is why it is rain. You can also call it as, it is a type of precipitation. Okay, so this is one way by which rain is formed. Another way also rain can be formed if if two oppositely charged clouds are meeting, then also there will be neutralization of charge. As a result, they will combine with each other and it will precipitate because of gravity. Fine. Now sometimes artificial rain is required, and in that case, how we can do so? It is possible to cause this artificial rain when we are throwing some electrified sand or spraying a sol which is carrying some charge, but it has to be that kind of charge which is opposite to the one that is present on the clouds. So in clouds there is some charge, suppose it is negative charge. Okay, so in that case we have to throw electrified sand or a sol which is having positively charged. Now these positively charged particles, they will neutralize these negatively charged particles. So it is like two oppositely charged clouds will meet to each other, and ultimately it will be precipitated in the form of rain. So in this way artificial rain also possible. Red and orange color of sky at the time of sunrise and sunset. So during sunrise and sunset we have seen only this specific color and any mixture of these, sometimes yellowish, sometimes more reddish, but never it is close towards any blue color, right? But when it is noon, afternoon, then we see that the color of the sky is either white or blue, right? So what is the reason behind it? So this is also under natural application of colloids. When the light is coming from sun, it is obviously traveling through earth atmosphere, and when it is traveling through this atmosphere there will be scattering before it is reaching towards us, because there is a long path it has to travel. Now this extent of scattering, it is not same for all the colors, so it may be different for different colors. Now if the light is of shorter wavelength, now shorter wavelength means high energy, and the colors are violet, blue, green, yellow, like this. So as we are moving, that is violet, blue, it is higher energetic even compared to green and yellow. So for this type of short wavelength color, what happens? There is higher amount of scattering compared to longer wavelength color, that is low energy, orange, red, like this. So scatterings are not same for higher wavelength and shorter wavelength color. So as a result, what happens? At sunrise and sunset, basically the sun is low on the horizon. So there is a long path that sunlight has to cover compared to the path when at noon it is completely above our head. So now the path is shorter. Look at this picture. Suppose this is at 12, that is noon, then this path, it is shorter compared to the path when at sunrise or sunset it is low on horizon. Now the path is larger. Okay, so here blue light is scattered more because it has to cross a longer path. So as blue light is scattered more, so mostly red orange, this wavelength will reach towards ground, that is towards eye, so we will be able to see only this color. Okay, see here yellow and red arrows are shown. These are only coming to us, but during the middle of the day here gas molecules scatter blue light more. Okay, and now the path is not very high, so the scattered light are directly coming to us, so that is why it is appearing blue. Fine. Now blue color of the sky as well as sea. Now blue color of sky, the reason we have already seen, but what about sea? The blue color of sky is because of scattering of the blue color by the sunlight, that is shown here. And also in case of sea, there is some impurities present in sea, that means in water medium, which is dispersion medium, some impurities, these impurity particles are basically colloidal in nature. So as a result there will be Tyndall effect. Remember Tyndall effect we have discussed, which is basically optical property of colloids. Okay, so when we have discussed Tyndall effect, it is in detail discussed that what is the reason behind this Tyndall effect. So now you can see the natural application of Tyndall effect. Okay, so because of the presence of this colloidal impurity, if the impurities are not of colloidal nature, then there will be no such thing, but as they are colloidal in nature, they can show this optical property which is known as Tyndall effect. Okay, as a result the color appears as blue. Fine. Applications of colloid in food and drinking water. So day-to-day life, in day-to-day life, every day that food we are actually consuming, they are also examples of colloids. Okay, and different types of colloids. Okay, because we have seen there is total 9 types of colloids, depending on what is the nature of dispersed medium, dispersed phase, different types of colloids are possible. Okay, so some are emulsion, some are gel, like this. Water purification, that is drinking water, how we can get. When it is impure water, basically it is a colloidal system, because impurity particles that are present, that are colloidal in nature. Now as they are colloidal in nature, ordinary filtration will not be effective, because the size of the colloidal particles are such, when we are using a normal filtration process, the pore size is such that the colloidal particles, they can easily pass through it. So that is why by filtration we cannot do the purification process. So one of the very popular method that is used for water purification is addition of some electrolyte, that is alum. Okay, so when we are adding this electrolyte, there will be coagulation, because we know that is a certain quantity of electrolyte is necessary for the stability, but if it is in excess, now there will be coagulation of the impurity. So that is why now there will be precipitation of these impurities, because the small particles will combine with each other, they will grow in size, and because of gravity now they will settle down, and clear water will be that can be decanted, or filtration can also be done. So in this way we can purify the water. Fine. So this is the application of colloids in foods and drinking water. Application in agriculture. So first we will talk about soil. When we are saying that the soil is fertile, basically it is colloidal in nature, and here humus is present, which is acting as a protective colloid. Now humus is basically the organic matter that is generated from dead plant and animals. Okay, these soils are mostly negatively charged. So obviously they will attract positively charged cations like calcium 2 plus, magnesium 2 plus, K plus in the outer parts of their double layer. Remember, double layer we have discussed, right? So if it is positively charged, it will be attracted by negatively charged. But mostly this type of soil, that is fertile soil where humus is present, then it is negatively charged, they will attract cations. Now these ions, that is calcium 2 plus, Mg2 plus, K plus, these ions are loosely bound, okay. The plant roots can absorb these essential nutrients. So see, this is very beneficial for the plant because of this attraction towards positively charged ions. Now these ions are essential nutrient for the plant. So they can be loosely bound in the double layer. So plant root can easily absorb them because we are talking about soil. So roots are in soil, they can absorb these nutrients easily. Similarly, these ions will be released in the soil, that is the revert process will occur when the plant is dead. Fine. So this is application in agriculture. Now formation of delta, though it is not agriculture, you can also exactly agriculture, but as it is related to soil, okay, so that is why it is discussed here. You can also consider it as if it is natural application of colloids, okay. But first we have to know what is delta. It is extensive deposition of sand and clay formed at the mouth of any river, that is the river when it is meeting with sea, falls into sea, at that region this delta is formed. So this is basically deposition of sand and clay. Now the river, why it is formed? Because river water mostly contains colloidal particles of sand and clay. This is negatively charged. See, here also you have seen soils are negatively charged, okay. But when we are considering salty sea water, it contains a number of positive ions. So see, again there is oppositely charged ions are present. So obviously when they will come contact to each other, these negatively charged colloidal particles of river, now it will be coagulated by the positively ions of the salt which is present in the sea, and this will lead to the formation of delta. So look at this picture. In sea water there is presence of salt and mostly NaCl, but other ions may also be present, Mg2 plus, K plus, Na plus. Now here this is the river water which is containing negatively charged sand or soil. Now these negatively charged particles, it will be coagulated by these positively charged ions. As a result, there is, actually it is having a shape like a triangle. This type of delta will be formed, right? Now some other applications of colloids. Medicine. Colloidal medicine. Medicine may be of different nature, okay, that is tablet, pills or liquid medicine. Now if the liquid medicine, when we are talking about, if it is colloidal in nature, it is basically more effective. Now the reason is, as they have large surface area, if you compare with true solution where the particles are very small in size, so obviously surface area will be less. But compared to the particles of true solution, if we consider colloidal particles, their dimension is higher, so surface area will also be high. So that is the reason, because of this increased surface area, their assimilation in the body, that will be very effective. Because medicines, better it is, that is higher is the assimilation, higher will be its effectivity. So these are the reason, that is a large surface area. This is the actual reason why colloidal medicines are more effective. Smoke screen. Smoke screens are used to hide something by a layer of smoke, okay. So this is intentionally made because it is applied in case of the movement of troops, so that they can hide, no one can recognize them, okay. So that is why we are calling it screen, smoke screen, screening that is made by the smoke. So this smoke screen, they are basically colloidal system, and here the particles that are used is titanium oxide. So here TiO2 is the dispersed phase and it is dispersed in air. So air is the dispersion medium. Okay, so smoke screen, it is basically used to hide movement of troops and it is colloidal in nature. Prevention of bleeding. Blood is colloidal solution that we have already seen, okay, and it is albuminoid substances, solution of this type of substances. Now this is actually a kind of protein, okay. Now when there is a fresh cut and bleeding is occurring, it can be stopped by applying a concentrated solution of FeCl3 or potassium. Now why it is so? Because blood is negatively charged colloidal system, okay. So obviously if we can provide positively charged ions, and see here valency is also very high, because we know according to hardy-Schulze rule, if the valency is very high for the oppositely charged ions, then coagulation power will be very good. So that is why if we can add these two, there will be coagulation and ultimately blood will clot and there will be prevention of bleeding. So here we have a fresh cut where these are the red blood cells. Now this is negatively charged, and when we are adding these Fe3 plus or aluminium 3 plus, all these are positively charged, so there will be coagulation, and as a result the blood which is present in liquid form inside the vein or any other capillary type of tube, okay, so it cannot come outside. So in this way blood clotting will be occurring and bleeding will be stopped, okay. Now we will discuss some problems. In this problem, we have 4 options, only one of them will be correct. The ability of an ion to bring about coagulation for a given colloid, it depends on what? First is size, magnitude of its charge only, okay, whether it is suppose +2 charge +3 charge, that means magnitude, okay. Sign of its charge, whether it is positive charge or negative charge, and the last option is both magnitude as well as sign of its charge. Now which of these is correct? Now the last example of blood clotting that we have seen, where the particles are negatively charged, okay. So obviously if we want coagulation, we will add something which is positively charged, otherwise coagulation is not possible. That means sign is important, because you cannot arbitrarily use any electrolyte or coagulating agent, because first you have to know what is the charge of colloid. If you do not know, how you will choose the coagulating agent? So once you know the nature, then you can choose it. So here sign is important because we require only oppositely charged coagulating agent. So sign is important. So is option C is correct, that is sign of its charge? No, it is not enough. Magnitude of the charge is also important. Because remember, according to hardy-Schulze rule, the valency of the coagulating agent, that is directly related to coagulation power. So higher is the valency, higher is the coagulation power. So if it is anything negatively charged, for example, you can also take the As2S3, arsenic sulfate. So for this, suppose we are using electrolyte containing Na plus or Ba2 plus or Al3 plus. So sign is important, that means all are positive, that is fine, but their magnitude is different. But magnitude also matters, because greater is the valency, greater will be the protective power. That means magnitude also we have to be careful. So which option will be correct? Both the magnitude and the sign of its charge. option D. Okay. Here we have a problem. A sample of charcoal having weight 6 gram. It is brought in contact with a gas which is present in 1 liter vessel. That is the capacity of the vessel. Temperature 27 degrees centigrade. Now charcoal, we know it has a capacity to act as adsorbent, so it can absorb this gas, right? So after bringing these two together, it is observed that the pressure of the gas falling from 700 millimeter of Hg to 400 millimeter of Hg. That means pressure is reduced, and it has to be, because now the gas particles are adsorbed on the surface of charcoal. So that is why now the pressure is reduced. Calculate the volume of the gas reduced to STP. That means calculate the volume of the gas at STP. It means at STP. That is adsorbed per gram of the adsorbent. That is per gram of charcoal under the condition of the experiment. Density of the charcoal sample given 1.5 gram per centimeter cube. Okay. Now here it is mentioned, calculate the volume of the gas at STP, but first we have to find out what is the amount of gas that is absorbed at the condition of the experiment, because when we are talking about the condition of experiment, it is 27 degrees centigrade, but when we are considering STP, basically it is 0 degrees centigrade. So both conditions are not same, but first we have to find out what will be the volume which is under condition of the experiment. Then we can convert it to STP by using PV equal to nRT equation. Okay. So this problem is basically combination of surface chemistry and also gaseous laws, because we will use the equation PV equal to nRT, where P is pressure, V is volume, N is number of moles, R is universal gas constant, T is temperature in Kelvin. Okay. Now when N, R, T constant, that is same. So under this condition, P1 V1 that will be equal to P2 V2, because this is constant. So at 27 degrees centigrade, here pressure is changing. So P1 and P2, these two values will be different. Okay. And here suppose initially P1 is 700 and V1 is 1 liter. This is V1, 1000 ml. This is P1. Okay. This is P2, but V2 is not known, so we will find out V2. So the equation will be P1 V1 by P2. 700, 1000 and P2 is 400. So from calculation you will get the volume, sorry, it is 1750. So here the adsorption is taking place, it is ml. Adsorption is taking place in a closed vessel and the vessel is 1 liter. So when pressure falls, that means it is correspondingly increase in volume, because from this relation, if pressure is decreasing, the other quantity, that is volume, it must be increasing. So that is why now see, the amount is 1750 ml. But if you are thinking that the vessel is 1 liter, then how this volume is possible? Actually it is possible because some adsorbent is present inside the vessel. Okay, so when pressure falls, there is correspondingly increase in volume. Now, as this volume is not possible because maximum capacity is 1000 ml, so to keep the volume constant, excess volume of the gas that will be adsorbed by the charcoal. Okay, so actual volume of the flux first we will calculate, because in the vessel there is volume 1000 ml, but remember charcoal is also present. If this is a container, there is also presence of charcoal. So without charcoal, what is the space that is available, that we will see. So this volume will be 1000 ml minus volume of charcoal. Now how we will get volume of charcoal? Mass is given 6 gram, density is given. Now we know density is basically mass by volume. That means volume is mass by density. Okay, so mass is 6 gram, density is 1.5. Be careful about the unit, it is also gram per centimeter cube. Centimeter cube means what? It is basically same as ml, that is cc. So no problem with unit. 6 divided by 1.5. This is the volume in ml or centimeter cube. Both are actually same. So 1000 ml minus 6 divided by 1.5 ml. If we do this subtraction, now you will get the volume that is available, and this value is 996. Okay. Now volume of the gas that is absorbed. Per gram of charcoal, that will be equal to, first of all subtract it from 1750 minus, so this is the available space. Okay, though it is 1 liter, but this is the available space, which is slightly lesser than the 996, slightly lesser than 1000. See, it is 996, that means 4 ml is only for this charcoal. So this available space, if we subtract from this volume, then we will get the actual volume of the gas that is inside the charcoal, that is adsorbed by the charcoals on the charcoal surface. Now this is the volume, but as it is per gram of charcoal, so we will divide it by 6 because mass is 6. Okay, so this value is 12571 ml. Sorry, it is 125.67, and finally we will change this volume at STP. Okay, that is what will be the volume at STP, because this is the volume at the condition of the experiment, but it is asking what will be the volume at STP. So to convert it, we will take the help of the equation P1 V1 by T1, P2 V2 by T2. Now it is possible because here N and R, these two are constant, because when you are changing the condition from reaction condition to STP, mole numbers will be same, there will be no change in mole number, and R is already constant, but temperature will change. So that is why, see, in the previous case we have used P1 V1 P2 V2 because at that time temperature is at 27, but now we are changing the condition from experiment to STP, so temperature obviously different. So that is why we have to use this equation. And here T1 is 27 degrees centigrade, which means 300 Kelvin. Then V1 is this value, 125.67. Then what about P1? P1 is 400. Okay, and what will be P2? P2 is 760 because that is according to STP condition, all are in millimeter Hg unit. and T2 is 0 degree centigrade, that means 273 Kelvin. So here which one is unknown? V2 is unknown. So V2 will be equal to P1 V1 by T1, then T2 by P2. Now if we put all these 5 quantities that are written here, the value of volume that we will get 6019 ml. Okay, so the answer is not 125.67 because we have to find the value of the volume, though here the line is little bit confusing. Okay, but it is actually trying to say that what will be the volume of the gas which is absorbed per gram of the absorbent per gram. Remember, it is not by 6 gram, it is by 1 gram, and the volume must be at STP condition. Okay, answer is 60.19 ml. The property of colloidal solution that their particles are charged. This fact is used in which of these? It is applied in which of these? Sewage disposal, smoke screen, delta formation. Now we have just discussed the applications of colloids, and in sewage disposal we have seen how we can clear the dirty water in gutters or drain. Okay, there will be coagulation of the dirt particles, and we can also get clear water. So these dirt particles, it will be used as manure, and clear water that will be used for irrigation purpose. So this is one application, that is the industrial application. Smoke screen, it is used to hide the troops. Okay, and delta formation, this is also a natural type of formation where river is meeting finally with sea, and the nature of the charge of the particles of colloidal particles of sea and the particles of river, these two are opposite to each other. So that is why delta formation. Delta formation is basically one type of coagulation. So basically we are using the charge. In all cases we are using the charge. Okay, so that is the reason that here property of colloidal solution where their particles are charged. This fact we are using. So here the property of colloidal solution that their particles are charged. So there are different properties of colloidal solution, but we have to focus only on the property of their charge. So basically coagulation of charge. Now in sewage disposal, coagulation is required, then only you can filter out the clear water, and in delta formation also it is because of coagulation. But if you consider smoke screen, which is used to hide troops, it is basically smoke particles, that is dust particles or carbon particles that is suspended in air. So here we are not using the charge, right? So that is why here all these are not applications of colloid where charge is basically utilized, but only in case of sewage disposal and delta formation, that is 1 and 3. So correct option will be this one. Which equation represent Freundlich's adsorption isotherm, which is a kind of physical absorption. Okay, so here we have 3 different terms, and we have to see which equation will be the correct. And there is also the option all of these, so all of them may also be correct. The first equation is, which is the original form of this Freundlich's absorption isotherm. Here K and N both are constant, and here X by M, this is basically the amount of gas, that is X, which is adsorbed on mass M at pressure P. So this is obviously the equation which is representing Freundlich's absorption isotherm. This is the original actual equation. Okay, so A is fine. Now if we take log both sides, so it is K into P to the power 1 by N, and log of, suppose X into Y, we know it is log X plus log Y. So here the equation will change to log K plus log P to the power 1 by N. Now 1 by n, it can be written before it because it is the power of pressure. So see, now the equation will be like this: log x by m, log k, 1 by n, log p. So this is also correct. Now the third one, the equation is reduced to x by m equal to k into p. So now as if n value is 1. Okay, and another equation, this is at low pressure. At high pressure, now it is very simple, x by m is equal to k. That means it is not dependent on the nature of it is not dependent on the value of pressure when it is high. That means here n is 0, slope is 0. Okay, so is it correct? And for that we have to know what is the graph, where that is the graph of x by m versus p. So in this graph, x by m in y-axis, p in the x-axis, basically you have to use this equation. Okay, so this is a kind of equation which is type y equal to mx, where m is basically k and x is p, though it has some power. It is not exactly this kind of equation, but it is close to this. Here we have a power, so that is why, that is power of the value which is in x-axis. That is why the nature of the curve, see, it is not exactly straight line. But up to this point, when pressure is low, up to this point pressure is low. Now see the nature of the curve, it is almost straight line. That means in this region, this x by m, that will be equal to k into p, because here slope is almost 1, because see, it is almost straight line, just like this type of graph. So this is correct at low pressure. Now high pressure, that means in this region, here the nature of the curve is such that it is almost parallel to x-axis. That means it is not changing with increase in value of p. So it means what? There is no effect of pressure, and that means here n value will be 0. That means 1 by n will be 0. Okay, and that means p to the power 0 is actually equal to k. So this equation at high pressure, that is also correct. So ultimately all these a, b, c, all these expressions are correct. So correct option will be option D, all of this. Okay.